Hi, what do shampoo, paint, and the metallic mirror finish on my sunglasses have in common? They all have to consider surface energy, and they were probably all designed with one or more surface energy techniques, like the ones we're going to talk about today. All right, we're beginning to talk about surface characterization, and I painstakingly made this fancy font to celebrate the day. I think the longest part of making this lecture was making the word surface characterization. If you're wondering what this image is behind, I usually kind of quiz people, what do you think made it and why? And or what instrument do you think made this image and why? And so maybe kind of think to yourself, what made this and why do I think this? I'll tell you what it is. It's a Mr. Clean magic eraser. And I find many uses for the Mr. Clean magic erasers. And they're quite wonderful little cleaning apparati, if you will. But you can kind of see the cellular structure, and the Mr. Clean Magic Eraser, it actually doesn't use any kind of detergent. It uses microabrasion, and you can kind of see the surface morphology of the sponge here. And so what I'm doing here is a very, I guess, qualitative analysis of the surface of a Mr. Clean Magic Eraser, and I used a scanning electron microscope for that. Surface energy is all around us, and if you take a look at this glass of water that I have, and I took the picture before I drank the water, so the water level is a little bit lower now, but you can see that there are some differences between the material and the bulk part of the water and then the top of the water. Okay, so there's a difference in the energy associated with the material and the bulk of your water compared to the energy of the surface. So you can actually visibly see it. So aspects like the meniscus, and you always hear the meniscus, and I remember like my chemistry friends would always tell me where to measure a liquid, and I would argue versus measuring at the top or bottom of the meniscus. And if someone can tell me the answer, I'd greatly appreciate it. But the energy of the surface is generally higher. And the surface energy is basically the difference of the energy at the surface compared to the energy of the bulk. And again, the surface of the surface, or the energy at the surface, is going to be higher than the two. Contact angle measurement is what we're going to talk about first, and it's pretty much the simplest type of surface characterization. And when I say simplest type of surface characterization, I'm not really giving it the credit it is due. But here's kind of the typical setup that we see for a contact angle measurement. You have kind of some drop of liquid on a solid, and then kind of exposed to gas. So typically air is where we do a lot of these measurements. However, if you're doing processes inside some sort of vapor deposition tool or something, you may need to alter the atmosphere, and that changes things considerably. But for this discussion, we'll just assume doing things in the open air. Contact measurement, angle measurement measures a term that we refer to as wettability. It's a pretty simple and inexpensive tool unless you're dealing with strange atmospheres. But it's a simple and inexpensive tool to get an idea of surface energy. And the angle is measured with an instrument called a goniometer. And a goniometer is basically anything that measures angle. One thing, and I kind of made this fancy animation so I wouldn't forget, and then I forgot it was there. How embarrassing. Contact angle is always measured inside the liquid. So I kind of have the little angle drawn here inside the liquid. It is always measured inside the liquid. Don't ever let anyone tell you different. I've actually come across different curriculum and different examples of people measuring the angle out here. And that's not correct. You don't measure the angle outside of the liquid. Young's equation is what we oftentimes think about when we think of surface energy. It's in other courses I know, and it was probably the first equation that I was exposed to as a young person. And it wasn't really until I got into industry where I started really paying a lot of attention to surface energy. But Young's equation is a pretty common mathematical operator or mathematical tool that we use for surface energy. One thing I need to point out, so gamma is generally the variable for surface energy, and SL is the energy between the solid and the energy between the liquid. So if I go back to this equation, or this slide, excuse me, liquid and solid. So gamma SL would be the interfacial energy. If you look, we have these other terms, gamma LG and gamma SG. And so SG would be between the solid and the gas and the liquid and the gas. We're taking gamma SG and gamma LG in most cases just to be the surface energy of either the liquid or the gas respectively. One thing I need to point out, sometimes keeping what contact angle means straight, like straight in your brain, can feel like you ran into a wall. And I've had several discussions with people over the years over what it really means. And I've had almost some arguments with different people, both in industry and academia, keeping things straight. You know, what does it mean when my contact angle is big? Okay, what does it mean when my contact angle is small? What does it mean when the water beads off of a surface? That kind of thing. And it is sometimes hard to keep straight. The convention of all this actually depends on your point of view, and I like the classic, they call it an optical illusion. I don't know. I kind of depend on, I think of it more as a point of view exercise. And so from one point of view, you see a wine glass. From another point of view, you see two people coming in for some besitos. All right. To try to keep the convention straight, you want to kind of look at this situation. So we have this question here. And I should have written solid, I apologize. So we have two solid substrates and we have two liquids. And we're assuming that these two materials are the same material. And we want to ask ourselves, which of the above liquids has the greater surface energy? And so in this case, we're assuming the same solid surface. And I'll give you a couple of seconds to maybe think about that. And hopefully you do not hear the activity outside my office while you think about it. All right, it would be this one. So for the same given solid surface, okay, the liquid that is beating up like this would have the greater surface energy. Okay, so this leads to some questions, right? Some problems with people's kind of understanding as to what surface energy means. And again, it all depends on point of view. And so this is from the point of view of the solid. So for a single solid, one type of material, if I have this type of behavior, the beaded liquid is going to have the greater surface energy. Now let's kind of flip things around. So now we're looking at the point of view of the liquid, okay? And again, I should have written liquid there, my bad. So we have two liquids, they're exactly the same. Okay, they're the same liquid, but now we have two different solids. So which of the above solid surfaces has the greater surface energy, assuming the same liquid? Okay, so think about it. Which of the above solid surfaces has the greater energy, surface energy, assuming the same liquid? Letting you think. This one. So it's a little bit opposite. So the greater solid surface has better wetting. Okay, so that's actually pretty interesting. And the analogy that's good to use is if you've ever glued two pipes together and I think the person who told me this was Bradley, so I have to give credit to the Brad man. When you're gluing two PVC pipes together, you want to essentially sand one of them. So you're effectively increasing the surface energy so the glue actually wets better. And actually, it's a little bit more complicated than that. You can get some complicated mechanical bonding and stuff like that. But the higher solid surface will the higher surface energy of the substrate or the solid surface will lead to greater wetting. Now here's the catch. Here's the kicker that always gets people. Interfacial phenomena. Okay, so which of the above solid surface interfaces has the greatest surface, and in this case, interfacial energy? Okay, so think about this. Which of the above solid surfaces will have the greatest interfacial energy? And if you understand this, then you really get the convention. Okay, so watch this a couple of times, laugh at the story of Bradley. But anyway, think about this. Which of the solid liquid interfaces has the greatest surface interfacial energy? I've repeated myself like 3 times, I think. Sorry. This one, okay? Wetting is an energy lowering process. Okay, so if I have a low contact angle, that means the interface is a low energy interface. And this is a high energy interface. So we've looked at it from 3 points of view. The point of view of the liquid, the point of view of the solid, and the point of view of the interface. If you can get it straight, I'm thinking my understanding is, for me anyway, if you understand what's happening with the interface, that's kind of the bigger deal, because you really want to know what happens when 2 things come together. All right, so if you get that this is a high energy interface versus this is a low energy interface, that's all you really need to get from this. To kind of help drive things home, I've done some experiments, and this is my honorary TA. She's my partner in Green Slime Crime, Isabella. And so we did some experiments in the kitchen, kind of drive home some of these concepts of surface energy. And the first experiment, and I didn't put in my animation, had to do with soap. Oops. There we go, excuse me. So we put a drop of soap, some pepper and water, and I'll even rewind it so you can see what happened again. And sorry I had a little technical error. We'll play it again. So we have pepper in regular water, drop a little bit of soap in the middle, and the pepper all goes to the edge, basically, and actually kind of starts going down, kind of on the edge of the bowl. And what happened? Well, I kind of gave the punchline a little early, but the energy of this in the center, okay, was dropped by the addition of the soap. Okay, this is kind of poor language or English on my part, so I'm sorry. When you have these kind of energy gradients, you start this kind of macroscopic flow phenomena from the low energy to the high area. So all the pepper is going to want to flow out, basically. And it's kind of cool. You can do this at home yourself. You don't have to use pepper. You can use oregano, kind of anything that floats. And just kind of showing you again. So that was the first experiment we did. And it's kind of cool. So it kind of shows the effect of adding soap to the surface energy. And one thing you have to kind of remember is soap is a surfactant. And surfactants, so if you don't know my background, I came from the semiconductor background before I went into academia. And I dealt a lot with solving yield limiting problems in making semiconductor chips. And a huge problem with making semiconductor chips was getting rid of the residue from the various processes. And so there was many, many clean steps. And surfactants are far and wide a very important aspect of the semiconductor process. So cleaning the wafers between steps is huge, because if you have residue from one step left over when you go and process another step. So if I have photoresist left on my wafer and I go and try to deposit titanium, I'm doomed. Okay, that titanium's not going to. All right, so soap is a surfactant. It's a fake word, surface acting agent. It's a molecule with two distinct sides, so hydrophobic at one end, hydrophilic at the other. The hydrophilic side is polar. Water is a polar molecule, so it kind of goes together. And I won't talk too much more about surfactants, but soap is a surfactant. We did some experiments here, and the green dots are water, so I did some food coloring, and let me try to make it a little bigger so we can see it. And there we go. I think that's a little better. And I should edit this better than this, but my apologies. So the red is, we've dyed it with food coloring, and water is, the green is water, so it kind of bubbles up, and the substrate here is wax paper, basically. And red is 70% IPA. It's really hard to find 90% IPA these days, I guess because of disinfecting or whatever. And you can see the water beaded, and we'll see what happens with the IPA. And so she's trying, it's a little hard for a kid to drop it. But you see there's a difference in the way the IPA behaves versus the water. And so going back to the slides now, we're not dealing with interfacial energy, but we're saying that we can actually say two different arguments here. So we can say the interface between the water and the substrate is a higher energy interface. We can also say, since we have the same substrate, that water has a higher surface energy than the IPA. Okay, so we can say that. So here we notice two different wetting characteristics. So the IPA actually wets better than the water. For the next experiment, we poked the water with a toothpick, and you can see poking the water with the toothpick really did nothing to the water. Okay, and so the water still has a bead. We're not doing anything to the energy. It didn't really do anything to the IPA, and the IPA kind of started coalescing a little bit, and but the toothpick didn't do anything. In the second experiment, we soaked the toothpick in soapy water. Oops, my bad. We soaked the toothpick in soapy water, and we kill the bubbles basically, or we kill the droplets. So we basically lower the surface energy of the water, we increase the wettability of the water, and we create an interface that's a lower surface energy. My daughter is very inquisitive, and so she wanted to do some more experiments. So she made these up herself, and so she wanted to see what happened when we dipped the soapy water toothpick into the IPA. And so nothing really happened because the energy was pretty much as low as it was going to get when we did that. And she really tried to do other stuff with it, but that's cool. So she dipped the soapy water toothpick in the IPA. The energy is already low. The interface is pretty much as low energy as it's going to get. So nothing happened there. Then she wanted to see what happened when we dropped IPA on the water versus what happened when we dropped the water on the IPA. And actually, this was actually pretty interesting for me. I'd never really thought to do this. And so she dropped the IPA on the water drop, and it pretty much obliterated it. And we repeated the experiment, and there is a difference in the mixing between dropping IPA on the water and water on the IPA. So we'll see dropping water on the IPA. So she was trying to creep up to it because we were trying to look at coalescence or cohesive energy. And so there's kind of two things. So let me pause it here. I'll rewind it a tad. So you see how the two droplets kind of come together? That's cohesive force, basically. So water has pretty good cohesive force. If you keep going, you'll see a difference in the water mixing with the IPA and vice compared to the other one. So here, there was a distinct interface between the water and the IPA. We didn't really see that when we dropped the IPA on the water. And you could argue because she used maybe a bigger volume of IPA on the water, but we kind of did this over and over again and kind of made a big fun mess out of it. And putting the IPA on the water totally obliterated the water. So it lowered the surface energy a lot. And here you still see it's almost immiscible, even though there is a mixing associated with water and alcohol. But it was really kind of cool. And I'm sharing this with you because this was an unexpected result. So it was kind of cool. We set up some experiments in the kitchen. My daughter then, kind of came up with her own ideas what to mix with what. And so kind of found some new findings that I honestly didn't really think about. I was mostly caring about soap when I set this up. So you've seen the all right, so now that we've taken a look at the experiments, we can kind of come back to the subject at hand, which is contact angle measurement. And so we look at our kind of schematic of the solid-liquid interface, and we have the surface energy of the solid. So here it's the solid and gas energy, so it's really the surface energy of the solid. Here is the liquid and gas energy, and then here's the interfacial energy between solid and liquid. So contact angle, again, I'm reiterating, contact angle is always measured inside the liquid, so don't ever forget that. So I want to pose this question to you now. Is Young's equation used to calculate the surface energy of the surface? Okay, and you could also say, is it used to calculate the surface energy of the liquid as well? So is it used to calculate Lg and Sg? Is it? Not generally. And the reason why is you would need to know the interfacial energy. For that, you would probably already know the surface energies of the substrate and the liquid anyway. Okay, so you generally do not use Young's to calculate the surface energy of a surface or the liquid for that matter. What you use typically is a more complex equation, and here's an example. And there's multiple equations that are used to do this, but this would be the Owens-Wendt-Cabelli equation, and so you have two components of surface energy, and this is assuming that you have the liquids known. So you have the surface energies of the liquids known. And kind of a little bit more detail about the Owens-Wendt, I think I pronounced it wrong, Owens-Wendt-Cabelli equation. Excuse me, I hope I'm not insulting anybody. I'm just horrible at pronouncing this. So contact angle is still important. This would be the total surface energy of the liquid. This is the surface energy of the liquid and the surface energy of the solid. However, we have these superscripts D, and we also have surface energy liquid solid and a superscript P here, okay? This stands for dispersive component, and this stands for polar component. So surface energies of substances are generally driven by the intermolecular bonding or interatomic bonding. And so we have polar and dispersive forces, basically. So hydrogen bonds and other dipole type interactions would be polar. And dispersive are like van der Waals, or also known as London forces. I've never actually seen people do this, but I'm guessing if you had an unknown liquid, you could use two known surfaces. And I've mostly seen people only calculate it based on known liquids. And there's a huge assay of data for liquid polar and dispersive surface energies, and I'm just going to suppose that there is for solids as well. I'm more familiar with liquids, so I'll just kind of throw that out there. Typically, I have people do this real time in class, and so here's a example problem of how you would go about calculating. Excuse me, how you would go about calculating the surface energy of a substrate. In this case, I'm speculating the substrate is Kodak photo paper, and in the past, I've brought photo paper to class and had people try to measure the surface energy of the photo paper. And so here's kind of an example. So you're working in a conductive ink factory. In my past life, I used to do a lot of work with conductive inks. And you want to document the surface energy of your inks. And so the substrate you're working with is Kodak photo paper. And so you need to know the surface energy of your substrate. Okay. So you need to do that so you can determine the surface energy of your liquid. And so the most logical step is to determine the surface energy of your substrate. And you have two typical substances to perform this task. Two typical surface energy measuring substances are water and ethylene glycol. You could also use various alcohols. So here's some tabulated data. And so you have a water and ethylene glycol. And so surface energy, I didn't make this clear on the previous slide. Your total surface energy is the sum of your dispersion and polar component. And the general units, generally accepted units these days for surface energy are millijoules per meter squared. So I probably should have had that information on the other slide. So you have your contact angle for water, and you have your contact angle for ethylene glycol. The dispersion component and the polar component are also tabulated. And so you can use this Owens-Wendt-Kibble equation to calculate it. You've measured your contact angle of your substances on the Kodak paper. And so you find that water has 53.8 degrees and ethylene glycol has 22.91 degrees. So let's go ahead and work through this. And you'll have to use some elimination substitution to do it. Right, so I'm going to work this out in a way that's hopefully helpful to everybody. And we're going to figure out the surface energy of our Kodak photo paper using the provided data for drops of water and ethylene glycol. And so the equation we're going to be using is the Owens-Wendt-Kibble equation, which is the total surface energy of a given liquid plus this term, 1 plus cosine theta, which is the contact angle, over 2. And this is equal to the dispersive components of the liquid and the dispersive components of the solid. All this to the 1/2. And I kind of messed up my parenthesis a little bit, my bad. Plus the polar component of the solid and liquid interfaces as well. And then let me kind of fix this. That's bad form. All right, so for water, we had some values. So we had 72.8 is our total surface energy of water. 1 plus cosine, and then the contact angle of water was a 53.8 degrees. And all of this term over 2. And so I need to make that a little clearer there. So all that term over 2 equals to 21.8, and then the dispersive component of the solid to the 1/2 plus 51.0, the polar component also of the solid. All that in a bracket. And there's some algebraic rules and stuff that if you don't remember, you can always go to Paul's online math notes. So I'll kind of work through it, just kind of thinking everything is cool. And so when you have this times this in a total bracket, it's just like saying 21.8 to the 1/2 times this term to the 1/2, okay? And I can simplify this number here is simplify it into one term, that kind of thing. So 57.89 equals to 4.67 times gamma SD to the 1/2. And I can add 7.14 times gamma SP to the 1/2. All right, so we've already taken the square root of 51.0. We can pull that term out and kind of show that. So we have one equation. So it's important to have two equations. Why? Because we have two unknowns, and hopefully you can read me my attempt to write on a surface. It's either this or a blurry camera. I am working on improving my technical capability to make these lectures, so if you have any suggestions, I'll take them. But anyway, I'm doing the best I can. So 4.67 gamma SD, and that's actually to the 1/2. My bad, I apologize. And plus 7.14 gamma SP to the 1/2. And that's equation 1. So for ethylene glycol, and we'll substitute it ethylene glycol, and hopefully this isn't too sloppy. I got 48.01 plus, and let me scoot it over because I don't want to run out of room, because that's always embarrassing. So 1 plus cosine 22.91 degrees, which was the contact angle of ethylene glycol on our substrate. And that's over 2. And that's equal to, and hopefully I don't run out of room because I'm writing so sloppy, 33.8 gamma SD plus 14.2 gamma SP, all in one bracket. And I'm not very happy with the way my handwriting looks. It actually looks worse than normal. But hopefully we'll be able to get some good out of this. So I simplified this. So I got 46.1 is equal to 5.81 gamma SD, excuse me, excuse me, double, gamma SC to the 1/2 plus 3.76 gamma SP to the 1/2. And so I can use elimination substitution for this. And I found that if I get rid of, what did I find? I found if I multiply equation 1 by negative 1.24, I can get rid of this term. So so this is equation 2. And I'll try to get a highlighter here. So we have equation 1, equation 2. So out of all my chicken scratch, and again, I apologize, I'm not happy with the way this looks. But hopefully you guys see what I'm doing. If I multiply equation 1 by 5, if I multiply equation 1 by negative 1.24, I can do some elimination. And so let me go back to pen. And if you've had me for other classes, I'm a sucker for elimination substitution for some reason. By negative 1.24. There's other ways to solve this. I remember the first time I taught this class, somebody did it in MathCAD. I mean, it was kind of cool. Much more elegant than this. But anyway, so you multiply equation 1 by negative 1.24. And let me make the negative a little more clear. And you get negative 72 minus 5.81 gamma s d to the 1/2 minus 8.85 gamma s p also to the 1/2. You add this to equation 2. So equation 2, you get, what am I saying? You get negative, because now you've eliminated the middle term here. So you eliminated the gamma SD, or the dispersive component of your Kodak paper substrate. So you get negative 25.89 is equal to negative 5.09 gamma SP to the 1/2. And you can work it out, but you get gamma SP equal to 25.87. And that's millijoules per meter squared. So don't forget the units. Units are very important. The final thing we want to do is plug it back in to one of our equations, because now we've solved for gamma SP equals 25.87. So we can plug it back into equation 1. And again, I apologize for this chicken scratch. I'll try to find a better way in the future. But you plug it back into equation 1. And so I have 57.89. That's supposed to be a 9. Whistling away. Equals 4.67 gamma SD 1/2 plus, sorry, excuse me, 7.14 times 25.87 1/2. I'll add in a step just to kind of do it. So you can kind of work along and do work along. You never know when these problems show up again. And oops, made a boo-boo. Equals gamma S D to the 1/2. So you solve for that. And so gamma S D then equals 21.33 millijoules per meter squared. So the total surface energy equals 225.87 plus 21.33, and I should be putting the units, so let me go back and do that. Plus 21.33, and that equals to, let me plug my calculator, plus 21.33, I got 47.2. And there you have it. So again, I apologize for the chicken scratch. Hopefully this is useful and you can follow along. If you have questions, always feel free to ask. And here are the polar and dispersive components. And then here's the total. Total is, oops, wow, that's kind of interesting, that effect. Okay, the total is 47.2 millijoules per meter squared. I think in a video I said 47.46, so rounding, I think I worked it out several times. But any questions, always feel free to ask, and we'll carry on with the lecture now. All right, so we've worked through it. We solved and we determined our dispersive component to be 21, or of the substrate to be 21.31 millijoules per meter squared, and the polar component to be 26.15 millijoules per meter squared. And so what's the total surface energy of the Kodak paper? Well, the total surface energy of the Kodak paper would be the sum of that, and I got about 47.2 millijoules per meter squared. And so the summation, surface energy total, dispersive plus polar component, and I worked it out, and I told you verbally 47.2, but my PowerPoint slide tells me 47.46. So who am I to argue? We're still in the 47 point something, 47 and change in terms of millijoules per meter squared. Interfacial energy now kind of becomes important because we kind of care about the interfacial energy, and it's what you really use Young's equation for. And so we ask ourselves now, what would the interfacial energy be between Kodak paper and our two liquids? Okay, so water and ethylene glycol. I worked it out, and we're really solving for and I'm real sorry about my chicken scratch, the gamma solid liquid for water is 4.46 millijoules per meter squared. So I just plugged it into Young's equation, and you can take a more closer look should you wish with it paused. And the surface energy for ethylene glycol is 3.24 millijoules per meter squared. And again, it's the same substrate. And so the ethylene glycol is a lower interfacial energy. So 3.24 versus 4.46 for the water. If we go back, we see that the water contact angle is 53.8 degrees, and the ethylene glycol contact angle was 22.91 degrees. So it had a lower contact angle, so that means it had a lower energy, and we've kind of seen this mathematically. Many ways, there's many ways to measure contact angle, and we'll talk about 5. So we have the Cecil drop method, which is the most common, the Whimley plate method, the capacitive air bubble method, capillary rise method, and tilting substrate method. Cecil drop, so this is the most common. You could say this is the dropper I used with the experiment on my kitchen table with water and wax paper. It's the most common. The contact angle is measured with a goniometer, and we've kind of talked about what a goniometer is. Here's an example setup, very simple setup. So you can buy really nice goniometers. Or you can do something simple like set up a camera on these are pretty common elevator stands, jack stands, I think are what they're called, scissor jack maybe, used in a lot of experimental setups. This maybe is kind of makes it look a little more grandiose, but you just set up a camera in front of the substrate, you try to keep it level so you can measure the contact angle. So simple goniometer setup. Wimley plate method. This is actually suitable for measuring the surface energy of fibers. So you can drip a fiber into a liquid and kind of pull it up so you kind of get some surface tension, and then you can measure the angle theta of the surface tension. You're still measuring the angle within the liquid. And this is also kind of cool because you're dipping it in a liquid. You could use a beaker or something, and you could actually control the temperature. So you could actually look at temperature effect on surface tension in a more controlled way. And another thing, this can be a dynamic test. So you can kind of dip it and pull it out and kind of look at different pull-out speeds and stuff like that and see if the angle changes. You could actually use a video camera. You wouldn't even have to use a static camera. Another method is capacitive air bubble method. And this is kind of a crude representation of it. But you can bubble in some air and you get an air bubble in there. And this is the only one that it looks like you're measuring the contact angle outside the bubble. But that's okay, because in this case it's flipped. So your gas is inside and your liquid's on the outside. So you're still measuring your contact angle in the liquid. Okay, so we're not violating my rule where I said contact angle is always measured in the liquid. This is another one where you could have temperature controlled liquid as well. And my bullet, if I actually read my own slide, the backwards measurement is measured outside the bubble, but you're still measuring inside the liquid. So we're still cooling the gang, so to speak. Capillary rise method, and this is kind of cool because it's used for measuring the surface energy of tubular materials. And I always ask this, I try to make this one interactive. How would you measure opaque materials? And it would be kind of hard, but you could use maybe some thermal imaging or some X-ray imaging system, or anything that could penetrate the tube. So even if you're using real thin tubes, you could maybe even use ultraviolet imaging. But anyway, it's used for measuring the surface energy of tubular materials, so capillary rise. I left the title off of this one, but it's the tilting substrate method. And so you have a leading and receding, or advancing and receding edge. And so you measure two contact angles, advancing and receding. I don't know 100% sure, but this to me seems like something that can measure the efficacy of wax. And this other one, Wimley plate method, you can use it for fibers. So to me, this seems like a method you would use to measure the efficacy of shampoo and stuff like that. Anyway, tilting substrate, so the surface is tilted till the drop actually starts to move, and so you measure two contact angles, the advancing and receding. All right, so surface energy measurement as done with contact angle measurement has many applications, and I talked about a couple at the beginning of the lecture. Cosmetics, shampoo, car wax, paint, any coating. It's put general metallurgy, thin films, print electronics, and many, many more. And so I've hoped you've enjoyed this little exploration, if you will, into surface energy and how you measure the surface energy of substrates. In subsequent lectures, we're going to talk about more, I guess, elegant, if you will, ways to characterize the surface of a material. Thank you very much and have an awesome, awesome day. Oh my. It's the end of the lecture. If you have any questions, you can email me at drobertson@utep.edu.